regularized linear regression. So a practical algorithm for building the 5 detector is going to be regularized linear regression. I'm going to keep it simple. We need a way to train this algorithm. We're going to use our good friend gradient descent. And so we're going to build a regularized linear regression trained with a stochastic gradient descent trainer. So all of that's going to make our 5 detector. So again, gradient descent offers a fast and easy, straightforward way to do this. Stochastic gradient descent presents certain disadvantages, right? So it's sensitive to feature scaling, and it requires careful tuning of a few hyperparameters to get it to work well. But we can do that through a pipeline in scikit-learn, right? So we can handle all of the scaling, the learning, the training, and bringing it back to the format that we need inside a pipeline. So let's look at some of the math of a regularized linear regressor. So let's say we have a labeled training set, right? Which again is going to be x of I. And that's going to be our input, and then y of I for each instance. That's going to be our target. Let's just say I equals 1 for a certain piece of data, and then m for the number of features that we have. So we can say that we want y of I to be positive 1 for a 5-digit, and 0 for not 5-digit. And our goal here is just to train the algorithm that allows us to get that. So again, kind of considering that we need to train our weight vector, need to train theta, we can go ahead and put together a cost function for that. So we're going to say j of theta is equal to 1 over m for each feature. I'm going to weight all the features the same. The summation of our feature for instance is equal to 1 for m, just considering one instance at a time here. And it's going to be the max of 0 or 1 minus y for that instance to the I times our theta value transposed times x, which is our input data for that particular instance, plus lambda over 2. And then we need our bias terms. I ran out of room, so I'm going to move this to the left. Which is the absolute value of theta 1, which is our very first term, however many we need, squared. So, and that's the first term is the hinge loss, which is part of the linear classifier, right? And then there's an L2 regularization term, which is on the back. And again, theta 1 is equal to our bias term. Right, and sometimes that'll be labeled as B, right? So if you look this up in other algorithms, they'll just label it as a bias term. I just put everything in theta. And that, our goal here is to minimize equation 3.4 with stochastic gradient descent. And that will yield an optimized classifier that will be able to put 5s into one category and not 5s into another. And this is done with stochastic, or let's say sklearn SGD classifier. And I point that out because it does not call it a regularized linear classifier. It just calls it a classifier because it's literally the most basic classifier that you can have. So sometimes people don't call it out by the full name. I like to call it out by regularized linear classifier because it just makes it easier for you to find source material or maybe like the math on